This is One Universe at a Time. I'm Brian Koberlein. Electric cars hold the promise of helping society conserve energy and wean us away from fossil fuels. But it's more complicated than that. On our show today is Dr. Callie Babbitt, an assistant professor of sustainability at the Rochester Institute of Technology. She's going to tell us why we need to consider the materials we use to build car batteries and how we will reuse those materials when the batteries reach the end of their useful life. One of the things you see a lot in the news is the Tesla electric car. Everybody loves a Tesla. Everybody wants a Tesla. It's one of these really cool things. And it brings to mind the idea that eventually we'd all love to have an electric car. You know, we don't want to be stuck with the gas companies anymore, and being able to just plug it in and charge it is this great idea if it can work. Everybody kind of sees that as a positive. And I think in your research, you're worried about the negatives.
I definitely, if I had $70,000 extra dollars laying around, first thing I would buy would be a Tesla. But at the heart of the Tesla are 7,000 lithium-ion batteries. And so the question that we're trying to answer is it good for sustainability to deploy electric vehicles, considering the batteries and considering the electricity it takes to charge them? Or are there potential downsides? And if there are potential downsides, what do we do now to mitigate those risks? So the key things that we're thinking about are, first of all, you know, when you take what we call a life cycle perspective, considering the entire system very holistically, is it more sustainable to charge vehicles with electricity or power the vehicles by gas? And a lot of that depends on where you're actually getting your electricity from. In the United States, we do burn a lot of fossil fuels. In some areas, less so than others. Like right here in Rochester, we use a lot of hydropower. If you're burning a lot of fossil fuels to make the electricity, there can be some downsides. But it also depends on the battery. So the farther you can go on a single charge, the more sustainable that the technology is. And so at the heart of this technology are lithium-ion batteries, which are the key for the future deployment of electric vehicles.
So part of it is how we're producing the electricity, and that if we are burning coal, for example, to produce electricity so that we can have electric cars, that's not really any different than just burning the oil directly. And maybe less efficient. Right.
I mean, the main difference is that when you're burning the gasoline in the vehicle, now your pollution is spread wherever the vehicle is driving. Right. If you're burning the coal, at least it's centralized at a single power plant, but that can have very negative impacts for the people who live around that area and for climate change, which is a global phenomenon.
Or we have acid rain, for example, in the Adirondacks because the Midwest burns a lot of coal.
Exactly. The sulfur dioxide produced when the coal is burned is converted to acid rain.
So this is a two-pronged problem in the sense that you have not only the electric cars that you have to produce and the batteries that go there, but then you also have to produce an alternative form of power. If you're going to say this is green, then you have to use either wind generators or solar panels or something like that.
And one of the tricky parts about renewable energy is that it is a variable source. You know, the wind is not always blowing and the sun is not always shining. And so batteries are essential for this technology as well. You have to be able to store the energy when it's being produced and then be able to put it out onto the electric grid when it's in demand. And those timeframes rarely match up.
I noticed one of the things that kind of comes out is there was, I think, an article that talked about how a Prius was worse than a Hummer or something like that in terms of its environmental impact. Is that kind of what you're arguing in the way things are now, or is it give and take?
Well, there are certainly trade-offs, and I think that while in the past some of these alternative technologies may have been viewed less favorably, they are improving at such a rapid rate that now there are, in general, some clear advantages over conventional vehicles, especially really poor fuel efficiencies like SUVs. Right now, in most parts of the country, in most of the electric grid that we're deploying, the electric vehicles typically come out on top. Okay. And then even with things like Prius, you have technology that's transitioning over time. So we used to use a lot of nickel metal hydride batteries, and now that's converting to the more efficient lithium-ion batteries. These batteries are up to 2 times more efficient than some of the conventional hybrid batteries, and 6 to 10 times more efficient than the lead-acid batteries that are in your vehicles right now.
I know your area is related to batteries and the waste stream that's dealing with that. I was reading an article that you were talking about where as we transition to electric batteries, electric cars, now we have far more batteries that we have to deal with. It's one thing to have batteries in our cell phones, but now we have these cars with a massive number. So there's going to be a spike in the number of used batteries that we're going to have to deal with.
It's a really interesting system. Right now, if you take your average laptop computer, you might have 6 or so cylindrical lithium-ion cells. Now imagine a Prius has 7,000 of those. So right now, the waste stream has a lot of these computer batteries, cell phone, tablet, anything electronic that you carry around with you probably is powered by a lithium-ion battery. The electric vehicles, on the other hand, the systems are much more large, carry a lot more energy, and have a relatively finite lifetime. Mm-hmm. So you can only use the battery until about 80% of its original capacity is left. And so the battery itself has a lot of life left, but it no longer meets the demands of used an electric vehicle. So it has to be able to give you a lot of energy over a long time and a lot of power when you need to accelerate quickly. Right. And so when the battery is at the end of that lifetime, what do we do with them? Right. In the U.S. right now, we don't have a recycling infrastructure, and we also don't have a reuse system because there's a lot of potential for these batteries then to be reused in other applications, like storing energy in the electric grid from these renewable energy sources.
So that's where that idea of using batteries in your house, these would be probably a way to use older batteries?
Sure, it could very well be.
If Tesla, for example, is going to make all these batteries, we've talked before about how companies have to take their own waste back. So Tesla is going to be responsible for taking these batteries back?
In the United States, there's actually no requirement yet that has to be done, although in Europe there are those kinds of manufacturer responsibility laws. New York State actually has a law banning the landfill of batteries, okay. Not necessarily vehicle batteries yet, although we see that might be a trend in the future. Companies should be proactively thinking about this. It also makes economic sense. So most of the materials that are in the batteries, the lithium, the cobalt, the manganese, are all extracted from mines outside the United States. Mm-hmm. So we're very dependent on importing these resources. And if we could develop a recycling infrastructure in the United States, then we not only have an economic system, jobs, but we're also securing a domestic supply of these minerals. So it would be in companies' best interest to think very proactively about recycling.
It seems like one of the things that we always talk about is that the batteries are always the Achilles heel. If we could just get better batteries, then we could do all these fun things with cell phones and cars and everything else. But as you said, transitioning from lead acid, for example, to lithium ion or nickel metal hydride, does it get harder to recycle as you go along? I mean, are you kind of balancing efficiency for waste?
All of the different battery technologies have unique recycling challenges, and lead acid is very commonly recycled in the U.S., but primarily because it's mandated. Lead, as we know, is a toxic, and so we have to keep that out of the landfills and out of our ecosystems. So because there's a strong regulation there, there's a lot of incentive for companies, there's requirements for companies to comply, right. Where that doesn't exist yet for lithium-ion batteries. And so it's actually a really interesting challenge because the valuable materials in the batteries, like the lithium, the cobalt, and the manganese, the nickel, and others, they're not yet recycled at a very high rate. We don't have a very good technology for doing this. They're also only in the battery in pretty small quantities, and the battery actually contains about half of its mass of non-recyclable materials like graphite and electrolytes and things like that. And so there's a small amount of material. There's a lack of technology, and because there's not yet a demand for these materials being used in new batteries, there's not a big market for it. Right. So we have to develop all of these areas at once to really build up this infrastructure. Right. And it will probably take some sort of environmental policy to drive it.
You can't just make money by recycling these things with the trace elements.
Not yet, although it could very well be in the future, especially as materials like cobalt become more scarce. There could become now better economic incentive for recycling.
And there's also the economic aspect of, because these are from all over the world, a lot of these are from unstable areas.
Right.
And so we could have fluctuations in those prices the same way we have fluctuations in oil prices.
Sure, or even trade restrictions or supply limitations due to different foreign policy.
Now, am I correct that most of the stuff comes from China? Is that
a lot does, although most of our minerals, have a truly global supply chain. And so at any given time, we might be getting these minerals from all around the world. But a huge amount of our lithium is in fact located in China, as is the case for many of the rare earth elements that you alluded to. So electric vehicles also have a huge reliance on other types of critical minerals. And these rare earth elements, which is a group of elements, not as so far rare in the total sense, but distributed around the earth in very low concentrations.
Right.
Only found in high concentrations enough to mine in certain areas. And some of these, like neodymium, is used in magnets that are used in the electric car motors. And so we also have to be thinking about the scarcity of these minerals as well.
It's one of the things that I find fascinating is that when we think of green technology in a general sense, we think that if we just do this simple thing, then everything will be fine. If we just go to electric cars, we'll stop burning fossil fuels and everybody will be happy. And you're kind of like the buzzkill in the sense that it's just kicking the can down the road a bit.
A lot of people think that sustainability is easy. It's a matter of just checking off a list of boxes like turn off the water, turn off the lights, or don't burn coal. But in fact, it is pretty complex. And that's why it's such a challenge to get a lot of buy-in around any given technology, because they all have trade-offs. That's also not something that we're necessarily teaching our future sustainability workforce how to evaluate. How do you actually compare the burning of fossil fuels with the scarcity of minerals? Now, there's methods to do that, but they're not widely communicated. And so a large part of what we're doing at the Sustainability Institute here at RIT is actually teaching these PhD and master's students how to evaluate those kind of trade-offs. The other point that I often like to make is that we should not always let best be the enemy of good. A lot of these technologies, while not sustainable forever, are also good transition technologies.
Okay.
So they might be a necessary stopgap until we get to the more desirable solutions at the end of the line.
Kick the can down the road and you've got a little bit more time to come up with a better solution.
Right. Because if we continue as we are going, I often like to say we will run out of atmosphere before we run out of coal. So there's not going to be a lot of barrier for us to continue to destroy the environment. So we have to begin looking for ways to efficiently solve these challenges while we can.
Do you think this is primarily kind of an engineering problem, or do you think it's more political?
Sustainability is truly an interdisciplinary issue, and we can create engineering strategies, but unless they're strategies that people want to buy, unless they cost the right amount that people are willing to pay, unless they're feasible from a social and a cultural and a policy perspective, they'll never fly. To create these sustainability strategies, we really have to then begin thinking about bringing in the engineers, the natural scientists, the physical scientists, the policymakers, economists, education specialists, even designers and people from fine arts who really understand how to get at user needs. It's a truly interdisciplinary challenge. But that also is what makes it very fun, because you're not stuck in a silo just working on a single widget or gadget that you're going to make. You're really solving problems that will affect the future.
Part of it, too, is the social impact. We think of a critical mass of technology in the sense that there are things that we are capable of doing physically, technologies that we can see on the horizon. But there's the whole social inertia in that the way we've done it is the way we want to do it. And so I know with electric cars, for example, I think it's a 300-mile minimum or a 350-mile minimum. That's what people want on a charge, because that's what a tank of gas will get you, is about 300 to 350 miles.
There's a lot of what we call range anxiety. Will we be able to drive as far as we were before, or will it really change our behaviors?
Right.
Maybe changing behaviors wouldn't be such a bad thing if it meant that we started developing our communities around more dense urban centers, so we were actually doing less commuting. But that can't necessarily force that kind of behavior change. But a lot of it is really communicating to the public, here's how this technology works, here's its limitations, and then at the same time deploying the right kind of infrastructure. So here at RIT, we do have several charging stations where folks can commute using their electric vehicles. The charging stations are right next to the building, so you get a prime parking spot, and then you're assured of a full charge on the way home. And other parts around the country are doing this as well. And even here in Rochester, many areas are putting in public charging infrastructure to enable this on the behavioral side.
And a lot of places are free. So you plug them in, you go to work, and then your boss is paying for you to have electricity.
Right.
So you don't have to pay for gas.
Electricity is still pretty cheap here in the United States, and for good and for bad. But that does enable us to charge our vehicles relatively cheaply compared to what it would cost to buy the gasoline.
You're listening to One Universe at a Time. I'm your host, Brian Koberlein. We've been talking with Dr. Callie Babbitt, Assistant Professor of Sustainability at RIT, about batteries in electronic cars. Batteries use a number of different rare earth metals. In our second half, Dr. Babbitt asked me where these materials come from and where they can be found in space.
Brian, we've been talking a lot about lithium-ion batteries for electric vehicles. It's a really interesting technology, and of course it's enabled by lithium as well as other minerals. Where does the lithium come from?
Lithium is one of these interesting things. If you look on the periodic table, you have hydrogen, helium, and lithium is number 3. And you would think that that would be something that would be very easy and very plentiful out there. But it's actually kind of an odd way for lithium to appear in the universe. In the early Big Bang, the early moments of the universe, 2 elements that were largely produced were hydrogen and helium. And there were trace amounts of lithium. So there was some lithium that was produced in the Big Bang. But one of the problems is that stars are fusing elements and they will produce heavier elements. So most of the elements come from stars. But stars don't produce lithium. They actually consume lithium. That's called lithium burning.
So it's actually consumed as part of producing the other elements.
Right. Lithium is so easy to convert to other things that as a star burns, it actually converts it to other elements.
All of these elements are then being formed in space. How do they get distributed or how have they been distributed where we find them on Earth?
When the solar system formed, the distribution of elements that we had is what formed the sun and the planets, as well as the Earth. And so the elements that were formed in other stars before the solar system came around are the elements that we have. But it gets a little bit more complicated because as planets form, for example, as the Earth formed, it was still very hot and still very liquid. It was magma. And so what will tend to happen is heavier elements will tend to sink down. And so things like iron and the rare earth elements, for example, will tend to go to the core. So your distribution on the crust, where we can get to it, depends upon geological activity, but it also depends upon what might hit the planet after it's kind of cooled a little bit.
So are there places on Earth where we know that there are deposits of certain elements that were there because of these later incidences?
There are places in which we can tell certain geological activity will cause certain elements to be closer to the surface. So one of the interesting things is in Canada, there was a large impact crater. And there are actually a lot of mines around this area. This meteor was large enough to basically melt part of the crust. And so it hit the planet, about 4 billion years ago, I think, and it melted a little part of the crust and things settled. So what happened is those elements concentrated.
Wow.
On kind of the basin area of the crater. So they're easier to mine.
Right, because they're easier to access.
Right.
Is the distribution of elements on Earth, how does that compare to, say, the distribution of elements on another planet? And why are they the same or different?
There are small variations. So one of the things we can do is, this is particularly in the asteroid belt, for example, because we can see lots of different elements in the asteroid belt. When you look at asteroids, they're all fairly similar in the broad sense, but the small variations, what you might call the chemical fingerprint, is different. And one of the things we found from the asteroid belt is that different groups of asteroids actually have similar chemical fingerprints, so they fall into same families. And so you can talk about different families of asteroids. That's actually one of the ways that we know that the asteroid belt was not of a planet that exploded to create the asteroid belt. It actually never formed into a large planet because all of these are chemically different. If it had been a planet that exploded, they would all be chemically similar, and then you wouldn't have the families.
And so are these different chemical fingerprints of these families, are they largely governed by when these elements were formed, or when these planets and stars were formed, or something else, the chemical structure, the conditions when they were formed?
In our solar system, they depend on where they formed within the solar system. So different planets will form at different distances from the sun, and because of that, they'll have different chemical compositions. In terms of stars, since stars form from earlier stars that have exploded, their chemical compositions depend upon the clouds from which they formed. So one of the things we can see in stars, there's a measurement of how many things, like how much stuff other than hydrogen and helium is there. And in astrophysics, basically the periodic table is hydrogen, helium, and then metals. And so we call everything else metals. And so the amount of non-hydrogen and helium is called metallicity. And you can measure the metallicity of stars, and we can see, for example, that older stars tend to have a lower metallicity. And so younger stars will tend to have more metals in them because they were formed from earlier stars. And basically the first generation of stars, what you'd call population 3, would only have hydrogen and helium. And then they would fuse heavier elements and other things. And then you would have stars form from them. Those would be population 2. And then you would have a star like the sun. That would be population 1. And the metallicity goes up with each generation.
Lithium and these other elements all have chemical properties. Mm-hmm. How are those influenced by these formation events and this kind of distribution?
The chemical properties are determined by the structure of the atoms themselves. So that's a chemistry aspect. How they form has to do with how much of different elements we have. So if we look at our bodies, for example, our bodies are made out of things like carbon and nitrogen and oxygen, and then hydrogen and the water. Those are very common elements. And if you look at the abundances, how many of different types of elements you have, carbon, nitrogen, and oxygen are actually fairly common. Not nearly as common as things like hydrogen and helium, but in the scale of the universe, they're fairly common. And that's because within the core of stars, one of the common reactions is called a CNO cycle, which is carbon, nitrogen, oxygen cycle. So it is a way in which hydrogen produces helium using a production of carbon, nitrogen, and oxygen. The common elements are actually the ones that are commonly produced within stars.
Oh, wow. And so it's not a surprise that then we would have such a large distribution of those in our bodies.
Exactly, because we are built from the things that are commonly available.
Right. One of the issues in sustainability we think a lot about is mineral scarcity.
Mm-hmm.
You know, there are some things that we will not be able to do in the future because we will run out of a certain element, at least in terms of ability to mine it easily and economically. Are there processes in the universe that are limited because of the availability of certain elements, or are they able to be sustained by continually fusing new elements?
Yes, there are processes that change as you get more metals. In the universe as a whole, over time, you're actually producing more heavier elements. Because as stars produce more material, when they explode, these large stars explode, those elements get put out there. And so early in the universe, you didn't have things like iron or oxygen or nitrogen or things like that. In the earliest points of the universe, the first stars wouldn't have had rocky planets, for example. So Earth is made out of a lot of heavier elements that can produce rocky materials. Hydrogen and helium can't produce rocky materials. So the very first stars wouldn't have had terrestrial planets. They wouldn't have rocky planets. But over time, as you get more elements, you can produce more rocky planets. And in fact, we can see a relation between the metallicity of a star and the likelihood of it having planets.
One of the things that gets a lot of speculation in my field is that when we run out of certain critical elements on Earth, we will go into space to mine them.
Right.
So if how likely is something like that, and where would we be looking to find these minerals?
The asteroids are actually a really good choice. Rare earth metals are not particularly rare. They're not the most abundant thing, but they're not particularly rare. And as you said in the earlier part, the problem is they're scattered everywhere. And the reason they're scattered everywhere is because the early rare earth elements were fairly heavy. So in the first formation of the Earth, they would have sunk towards the core. So the ones that we see by the crust were actually deposited later by things like comets and meteorites. As you have these meteor bombardments, they would scatter these elements across the surface of the Earth. So they're pretty randomly distributed. So even though there's quite a bit of it, they're not concentrated in ores. So if you go to the asteroids are rich with these rare earth elements. I think there was a basic calculation that if you took a single asteroid ripe for the picking that's 500 meters wide, it contains more rare earth elements than have ever been mined on the planet. So if we can get to it, and if we can mine it, then we're good.
And how likely do you think it may be that space technology may actually be motivated or incentivized by this desire or an economic need to explore for more minerals?
I think once the technology gets to the point where it becomes affordable to go into space, then you will absolutely find that mission of going towards commercializing it, because the stuff is out there and it's commercially viable if you can get there feasibly.
How do we know about the likely concentration of these materials or the metallicity of certain planets or stars? Is this something that can be observed optically, or is this something that's modeled through foundational empirical evidence here on Earth?
It depends on different things. So one of the things we can do is we can look at the spectra of reflected light off of an asteroid, for example, and the light that it comes off of depends upon its chemical composition. So we can get an idea of what elements are there and what the strength of those elements are. In terms of things like asteroids, we also have meteors. We can look at meteorites and we can measure what their chemical compositions are. The patterns of those will match certain asteroids. So not for every case, but there are certain meteorites in which we can look at the chemical composition and match it to a specific asteroid. So we know they're part of the same family. We can do the same thing with Mars. We can look at the composition of Mars, and we have some asteroids that we know chemically came from Mars.
So in terms of these observational-based methods, what are the techniques that are used? What are the types of analytical equipment or observations that are used?
On Earth, you can use things like mass spectroscopy. You can actually vaporize a small bit of the material and then run it through this device that will distinguish different elements in the abundances. That's a lot more chemistry than where I am. I just look at the data and say, oh, look, that's what it says. Okay, fine. Thanks, chemist.
Right.
And then I look at something else. We've gotten really good with things like asteroids of taking very precise measurements, not only of what elements, but what isotopes of elements. And that's one of the ways that we can tell, for example, the moon. The moon is very chemically similar to the Earth, but there are specific isotopic differences. And those differences actually help confirm that the moon was formed from a large collision, that a young Earth was collided with a Mars-sized planet, basically, not Mars, but a Mars-sized planet, and caused the splitting into an Earth and a moon.
And so what kinds of isotopes do you look for to determine something like that versus another mechanism?
It depends on the different elements. Oxygen, for example, is a good one. A different one would be in water, for example. Water is H2O, and hydrogen is a proton and electron, and then oxygen is its element. But there's a variation of hydrogen called deuterium, which has a neutron. So it's a proton and a neutron with an electron. Because it has a neutron, it's slightly heavier. Deuterium water that has deuterium instead of just hydrogen, is slightly heavier. So it tends to evaporate less. Mm-hmm. So you can actually look at things like on Mars, you can say, let's measure the deuterium ratio to hydrogen ratio in the ice on Mars. And what we find is it's concentrated. And because of that, we know that Mars at one point had a large liquid ocean and that it evaporated off, and most of that was hydrogen. Most of the deuterium stayed. So a concentration of deuterium shows that Mars was actually once a wet planet.
Oh, that's fascinating.
So these little isotopes make a big difference because that slight difference in mass can affect things like evaporation rates, formation rates in minerals, and things like that. We've been talking with Dr. Callie Babbitt, an assistant professor of sustainability at the Rochester Institute of Technology. Our program is produced at RIT by Mark Gillespie, with support from the RIT College of Science. I'm your host, Brian Koberlein. Thanks for listening to One Universe at a Time.